Howdy. Today our topic is serious, a flat data center network with nanosecond optical switching. We will follow this order for one presentation: background, overall system understanding, detailed explanation, results, and discussion. First, let's introduce the background. A data center is the foundation of cloud computing. I believe all of us already know that. Like this picture shows, it contains many levels of servers that communicate with switches. These switches determine the next node for each packet in a complex network. Most data centers today use electronic switches with their functions handled by the CMOS chips inside the switches. CMOS chips, hearing this, we know that electronic switch performance is also limited by Moore's law. So this is the problem, right? As shown in this graph, data center network capacity is growing even faster than Moore's law. To keep up, we have to build larger data centers, which lead to higher power consumption, additional latency from more network layers, and increased operational complexity. So a possible solution for this is to use optical switches. This is a rapidly developing area that doesn't rely on chips. It routes data using optical components. This diagram is an example. By rotating a mirror, we can split light in different directions. But can we simply replace existing electronic switches with these optical ones? The answer is no for two main reasons. First, these switches have moving parts, meaning they can't operate very fast. Achieving ultra-fast operation on a mechanical level is really hard. And routing speed, in a sense, determines your latency. It has high latency. Second, traditional switches can perform internal computations for things like congestion control, time synchronization, or something like that. But with optical switches, if two data streams collide inside the switch, light can't just be stopped, right? Those data streams would crash and be destroyed. The control logic for passive components and computation-capable components is entirely different. We need a complete set of protocol to ensure efficient and reliable data transmission. So we can use this analogy. Traditional data centers are like expanding highway interchanges. If you've ever driven on something like the Katy Freeway in Houston, you understand the frustration. Every time you double the width of the road, the number of cars may triple. And as more roads are added, the complexity of the interchanges grow almost exponentially. You will notice the roads are getting wider, but the traffic is getting worse. So our goal is to move away from the traditional approach and develop a citywide metro system instead. The optical switch here is our transfer station, but beyond that, we also need to build the trains, the lines, design the roads, create scheduling measures, and set up the entire structural framework. So now let's take a quick look at what the system in this paper actually looks like. Each server has several fast-tunable laser sources and can receive light at a specific wavelength. Tunable here means that the laser source can generate light at different wavelengths. When the light passes through the component called an AWGR, different wavelengths are routed onto different paths and sent to their respective receivers. And there are some clever control logics involved in making this work. To sum up, this paper presents 5 core technologies, 2 related to hardware and 3 to architecture. Our main goal today is to walk you through these 5 technologies. Fast tunable lasers is our high-speed trains. AWGR is our transfer stations. And we need to design the road and design something about congestion control and time synchronization. In the following sections, we'll explain why each was chosen or designed, how it works, and what advantage it brings.
We will start by discussing the two major building blocks of series architecture. On the server side, we have the tunable lasers to select wavelength of emitted light. The second component in the system is the AWGR router that routes the input wavelength from the server side to the specified output destination server. This establishes a route between server and destination. The output port receives the wavelength from AWGR to further communicate with the input server. These two components together help achieve the nanosecond optical switching and server communication in the series architecture. The AWGR or Arrayed Wavelength Creating Router works on the principle similar to light dispersion. Here, each dispersed wavelength is directly routed to a specific output port. This setting does not include any electrical or mechanical moving part that may introduce propagation delay or latency. Now, this is of great advantage as it does not require any power or component movement, which is why it is highly reliable as compared to the electrical switches used earlier. Moreover, this makes the routing automatic and fully passive in nature. This also provides an all-to-all connectivity between input and output ports. The all-to-all connectivity is achieved using the cyclical routing application in AWGR architecture. For example, as shown in the figure, the same wavelength lambda1 when sent from different input port end up at different output port. Now this is done using the modular wraparound to achieve cyclical routing of input wavelength to all the other output ports. But now the question is, how do we select the correct input wavelength to choose an output port? This is where the tunable lasers come in. Tunable lasers are a combination of gain section and grating section. Here, the gain section is what generates a range of wavelength, and the grating section helps to select one wavelength from the range of wavelengths. Specific wavelengths are selected by adjusting tuning current in the grating section. The grating section then allows a wavelength to exit the laser. This helps the input server to dynamically choose its output server just by shifting their wavelengths. For example, server A can communicate to server D through wavelength lambda 4, and the wavelength can then be tuned to lambda 7 to communicate to server F. This reconfiguration of wavelength to change output server is achieved using tuning current in the laser. But this sudden change in current introduces a ringing effect that is similar to one shown in the figure. When we strike a tuning fork, it oscillates before settling to a stable position. Similarly, the wavelength oscillates around a stable position before settling down. This causes a delay in the reconfiguration in order of milliseconds. So how do we reduce the reconfiguration time? One solution to tackle the ringing effect is to introduce a damping effect, where we overshoot and undershoot the current in a controlled setting and then slowly reach the stable wavelength. This helps to bring the reconfiguration time to 14 nanoseconds, which is a great improvement, but the architecture aims to get this time under 10 nanoseconds. To further reduce this time, we introduce a disaggregated tunable laser where the gain section and the grading section are independent of each other, which eliminates the observed interference and reduces the tuning latency of the system. We'll start by discussing one of the disaggregated tunable laser, which is the fixed laser bank that has multiple independent lasers to emit different wavelength, and SOA or the semiconductor optical amplifiers are used as on and off switches or optical gates for respective wavelengths. This helps to tune and change wavelength and switch SOA within nanosecond without any interference. The other two architectures are as follow. Tunable laser bank work on the principle that the upcoming sequence of wavelength is known in advance so that the lasers can be tuned efficiently to reduce the latency. The limitation here is the complex control system and the next wavelength must be known in advance. Another architecture is the comp laser architecture that generates equally spaced wavelength and uses SOA switches to select a particular output wavelength. COM lasers have shown improvement in wavelength configuration time from 14 nanoseconds to 0.9 nanoseconds, which is a great improvement as compared to earlier. In this paper, we will mainly focus on fixed laser bank in the upcoming series architecture section.
Architecture. Series is tunable lasers plus gratings which acts like an optical switch. It can connect multiple nodes in a data center to form an efficient network cluster. Physical topology. In series, multiple nodes are connected to a central series network through optical fiber cables. The nodes communicate with other nodes through tuning the wavelength of their tunable laser. Depending on the wavelength received, the grating directs that data to the corresponding node. Each node can reach different groups of destination nodes by tuning its laser to the correct wavelength. This network architecture makes it possible to scale it to thousands of nodes. Since we use optical fibers, it's very fast and nodes can directly connect to other nodes in one step. But nodes only have direct links to a particular subset of nodes. Therefore, the authors propose a routing mechanism to effectively route data to other nodes. A major advantage of Sirius is that no queuing or packet processing is required inside the central network, but is performed at the individual nodes, thus making it more efficient. However, a node can receive data from multiple nodes at the same time. In common networks, there is a scheduler that decides which node will send the data by considering the traffic, but it takes a lot of time. To avoid this, Cirrus uses a schedulerless design, where a fixed schedule is implemented and every computer knows in advance when and where to send data. This is a repetitive process and it ensures equal bandwidth to all nodes. How does the data transfer take place? Every node tunes its laser to a particular wavelength, where every wavelength connects to a different group of nodes and transfers or receives the data. In the next cycle, the laser is tuned to a different wavelength. All nodes follow the same cycle and therefore no two nodes send data to the same node simultaneously. This ensures that all nodes get equal bandwidth and no node waits for too long. This eliminates a central controller, making the system faster and simpler. Data moves smoothly across the network as everything is well organized and pre-planned. Cirrus uses fixed-sized packets for transferring data. In server-based setup, each server transmits data packets. If the packet reached its destination, the server accepts it, otherwise it sends it further. In a rack-based setup, if a wants to send data to another server in the same rack, it sends it directly through the rack switch. If it wants to send to a server in another rack, it puts in a FIFO queue before sending to another rack. This ensures a packet takes only one extra hop before reaching its destination and is not confined to only a few routes for reaching the destination. Since the data has to pass through an extra node, there is a delay. However, Sirius's load balancing method ensures that even in the worst case, the speed is only up to 2 times slower than an ideal system. To increase the data transmission speed, they double up the uplink connections. When multiple packets arrive at destination, they are queued, hence this also increases the latency. Since the data packets travel through different nodes, they are delivered out of order. But because of the network's efficient traffic management, only a small buffer can handle this issue. To avoid queuing of data packets at nodes, Cirrus uses a congestion control protocol and prevents large delays in traffic transmission. It's a four-step process. Buffering, where each node has a buffer called local, where the data packets generated by itself and received by others are stored. Request. In every epoch, the node sends a request to an intermediate node only once per epoch, asking for permission to send the data packet. Grant. At the same time, every node looks at the request it's received in the previous epoch. If the number of queued data packets in its buffer is lower than a threshold, then it grants permission to send the data to the node. This avoids overloading of traffic at the node. Sending cells. Once a node receives a grant, it then transmits the data packet in the next epoch. Because of congestion control, there is low and predictable latency. It prevents queue overflow and therefore ensures that no packets are lost. Time synchronization. In series, due to fast optical switching, everything happens in nanoseconds. Therefore, synchronization between different nodes is crucial. The existing synchronization methods are not sufficient or are so complex that they require specialized hardware. Instead, Sirius takes advantage of its passive core and cyclic schedule for efficient synchronization. Each node extracts the timing signal from the data it receives and matches itself to that clock frequency. A leader node is chosen and it sends the main time signal. Then other nodes adjust the clocks according to it. The leader is changed in every epoch in a round robin manner, which prevents failures. If a node fails, it is automatically replaced by another node within a few microseconds, and this prevents any significant clock drift. Overall, small differences in clocks can cause errors. However, in serious, clock drift doesn't matter as long as nodes are synchronized relative to each other. Sirius also considers the physical distance of the nodes from the AWGR central gating, since the farther the node, the longer the data will take to arrive. It then accordingly adjusts the start time of the epoch for each node. The farther the node, the sooner it will start transmitting, and the data packets from all nodes arrive at the same time. This ensures synchronization. A few other design aspects of Sirius: CMOS dependency. On a server-based setups, we can have non-CMOS-based network up to a few thousand servers, whereas in rack-based Sirius, CMOS are still required for interact connectivity. The design of Sirius allows for parallelizability to make it more efficient. End-to-end reconfiguration latency. After every epoch, there is a small break called guard band, during which no data transfer takes place. In this time, nodes adjust their clocks and recover incoming data. When the two nodes are interconnected, it takes time for them to synchronize their clocks. Usually, this process takes microseconds, which is a major problem. To avoid this, Sirius uses cache, which remembers previous clock settings instead of relearning them, thus reducing the latency. It also uses amplitude caching for adjusting optical power levels without slowing down. Laser sharing. As light travels through the network, its power reduces. This is called insertion loss. To make sure the signal reaches its destination, the lasers need to produce sufficient power to ensure signal is strong enough. But the commercial lasers can produce up to 40 megawatts of power, and therefore only one laser can be shared by up to 8 transceivers. This greatly reduces the number of lasers needed, which in turn reduces the cost and power consumption while keeping Sirius fast. Fault tolerance. Sirius network uses no moving parts or electronics that can fail. Hence, it's very reliable. The lasers are more prone to failing, but they are easy to replace and backup lasers can be shared, which reduces cost. However, failures can still happen. In Sirius, since the traffic spread out across all nodes, a failed rack can impact all nodes too, as their data also passes through the failed rack. But for tolerating fault, Sirius checks connections every few seconds, microseconds, so failures are detected very quickly. When any node fails, the system immediately alerts all other nodes to not pass traffic through the failed node. The system automatically adapts to the failed node to ensure the smooth running of operations.
In this section, I will show the cost analysis for series and the cost comparison between series and the baseline model. In this paper, the authors choose traditional electrical switched networks ESNS as a baseline model. Here is a setup for the comparison. Noticing that series applies a single layer of passive AWGRS and tunable lasers. We first show power analysis. The result is shown in this figure. The axis is the ratio between the tunable and fixed laser's power consumption, and the y-axis is the ratio between series and the baseline model. We can see that the series apply tunable lasers, which consumes more power than fixed lasers. Series still consumes much less power than baseline model. This is because first, series eliminates core switches and multiple transceivers, and the second, the passive AWGRS consume no power. And now we show the cost analysis. We assume tunable lasers cost 3 times larger than fixed lasers here. As shown in this figure, we can see series enjoys much less cost compared with two kinds of ESNS, the non-blocking and the over subscribed. So now we briefly introduce the prototype implementation for series. The author proposed two-generation series. We can have a look at the picture. The part A shows a series node and the prototype includes 4 nodes. Next, we show the simulation results. This is a setup for the simulation. Those setups are standard, and the author also choose ECSN as a baseline model. The result shows that series significantly reduce 99% flow complementation time for short flows, up to 86% lower than oversubscribed ESNS, and matches non-blocking ESN performance at high loads, with only slight overhead at low loads. It also delivers near identical coverage server good put to non-blocking ESNS and outperformance over subscribed ESNS by 6.7 at high loads. In this paper, the authors propose a novel network architecture series, which uses fast tunable lasers and passive wavelength gratings to achieve nanosecond scale reconfiguration. By eliminating core switches and introducing a new mechanism, series provides high throughput, low latency, and significantly reduced power usage compared with the existing architecture. However, there are two main shortages for series. So the first is static scheduling limits flexibility. Series relies on fixed timetable for scheduling, which implies the system, but which simplifies the system but makes it less adaptable to bursty or irregular traffic. So one possible solution is that we can introduce partially dynamic scheduling windows to enhance flexibility while maintaining global synchronization. And the second shortage is that phase caching may be unreliable in large-scale deployments. So the phase alignment might drift significantly due to hardware variability or environmental factors, and the cache values can become invalid. So one possible solution is that we can develop more robust fast synchronization mechanisms. Yeah, that's all. Thank you.